Okay, Assalamualaikum warahmatullahi wabarakatuh. Now, in this video, I am going to continue with our discussion on the chapter of thermochemistry, and we are going to talk about Hess's law. I hope you still remember that Hess's law is based on the first law of thermodynamics, which states that energy cannot be created nor destroyed. We can only make use of the energy that is available to us by God's creation and to harness it, and we can only convert it into different types of energy. And based on this law, Hess's law is formulated, and this law is used to calculate the enthalpy changes of certain reactions that cannot be determined experimentally. Now, the data that we use in this calculation is based on reactions that can be measured experimentally. Now, this is due to the fact that most chemical reactions occurs in several steps, and basically the total enthalpy change of each step is equivalent to the sum total of the change from the initial step to the final step. So this is what I've mentioned just now. Not all reaction can be determined directly, and Hess's law is applicable to determine enthalpy change of reaction for reaction that occurs in a series of steps. The enthalpy change of an overall process is the sum of the enthalpy changes of its individual steps. So this is the equation, or the summary of this law. Now, so the simplest method that you can actually use to calculate the enthalpy change of a particular reaction based on the available data is the algebraic method, which I am sure you will remember, whereby we use the available data. For example, in this reaction here, we want to find out the enthalpy of formation of sulfur trioxide. That means the enthalpy change when 1 mole of sulfur trioxide is formed from 1 mole of sulfur and 1.5 moles of oxygen. Now, the available data that is given to us is the reaction between sulfur and oxygen forming sulfur dioxide. Delta H equals negative 296.8 kilojoules, and another data is when 2 moles of sulfur dioxide reacts with 1 mole of oxygen, forming 2 moles of sulfur trioxide. Delta H equals negative 198.4 kilojoules. Now, basically, the method is that we have to rearrange the equation so that we can get into the final form of the reaction that we want to calculate. Yeah, if you can see here, we want sulfur and oxygen to be on the reactant side, right, and sulfur trioxide to be on the product side. So we might have to reverse the equation if we need to do that. So we see here, we don't have to reverse the equation, or we don't have to change, because from the data given, the data that we are given is that sulfur and oxygen are the reactants, and sulfur trioxide is the product. But here we have to calculate the enthalpy change given based on the number of moles needed. Yeah, the data given here is for the reaction between 2 moles of sulfur trioxide and 1 mole of oxygen, forming 2 moles of sulfur trioxide. Now here you can see that we only need to have 1 mole of sulfur trioxide and of sulfur dioxide and half a mole of the oxygen. So therefore the enthalpy is half of the data given. Now once we have done that, we total up delta H1 and delta H2 to get delta H3, which is the enthalpy value for the reaction that we need to calculate, which is here in this case it is negative 396.0 kilojoules.